Okay, so this is problem 2.5 out of Griffiths' Introduction to Quantum Mechanics. Before I get into actually solving this problem, I wanted to ask you guys if you wouldn't mind liking this video and subscribing. It's a very easy and free way to support me. And I post a lot of videos like this, posting solutions from popular undergraduate textbooks. So I think I post a lot of material that you may benefit from if you're interested in this video. Okay, now let's get into the problem. So we have a particle in an infinite square well that has an initial wave function as an even mixture of the first two stationary states, as given there. And we have a bunch of different problems here. We need to normalize our initial wave function. We need to find our total wave function and the modulo squared. We need to compute the expectation value of x, noting the amplitude of oscillation and the frequency of oscillation. Then we need to compute delta P, and then we need to talk about the different energies that could be measured from the system. So problem A, I think, is pretty straightforward. That's annoying. That happened in a previous video as well. So I hope this doesn't become a common occurrence, but I have a feeling it will be. So I'm just taking the complex conjugate of our wave function, and now I'm going to multiply it by our regular wave function. And remember, our normalization condition states that this integral has to equal 1. Now we can break this up into a sum of different integrals. So the first one, psi 1 star psi 1, that's just psi 1 squared. Then we have psi 1 star times psi 2, and then same thing but reversed. So that's the integral from 0 to a, psi 2 star x, psi 1 of x, dx, plus, and then using the same rationale before, this is the modulus psi 2 of x squared dx. This all needs to equal 1. Okay. Well, we know that this integral is just 1, right? The probability of our first state being somewhere in the wave function, that's a guarantee. That's essentially our normalization condition. Here, we can use our orthogonality relationship. Psi 1 and psi 2 or orthogonal of to each other. This integral is 0. For that same reason, this integral is also 0. And just like how the first integral was 1, this one is also 1. So without having to solve any integral, we know that the sum of these integrals is 2. So 2a squared equals 1. Or solving a equals 1 over the square root of 2. Not bad. Let's move on to part B. Let's remind ourselves what part B is asking for. Find our total wave function and the modulus squared. It gives us a hint to let omega equal pi squared h bar over 2ma squared. And it says express the latter as a sinusoidal function of time, as in example 2.1. So that would be a good one to look at if This one's a little tricky for you, but let's go ahead and work through this. So all that I'm doing here, there's this A constant that is in our initial wave function, and I'm going to just pull that out, 1 over root 2. And now what I'm going to do, I'm going to multiply each state, so in this case psi 1, with the e to the minus I e1t over h bar. This is the time dependent part. If you remember in section 2.1 where we broke our wave function up into a time part and a position part, we're going to do the same thing with psi 2. No problem there. Now I'm going to remind you of an equation in our textbook, which is the nth state for our time independent Schrodinger equation is equal to the square root of 2 over a sine of n pi over ax. Because remember, this is still an infinite square well. So this is our wave function for this. So we can substitute those in, but we're also going to do this omega substitution that the problem recommends we do. The problem gave us this suggestion. And to me, this looks very similar to an energy equation for the infinite square well, because the nth energy state with this form is, let's see, h bar n squared omega. I think I got that right. So then E sub n divided by h bar is then just equal to n squared omega. So E1 divided by h bar, you're just plugging 1 in for the n, that's just omega. And E2 divided by h bar is, so 2 squared is 4, so that's 4 omega. These can be plugged into these energy states. So we're going to plug those in, and we're also going to plug these different guys in. So what do we get? Well, we have our 1 over root 2 still. But now each term has a root 2 over a from our wave function. So then we have the first state where n is 1. This will just be pi over ax e to the minus I omega t plus sine 2 pi over ax e to the minus 4I omega t. So really, I think that's actually technically what B wants, but because we need to find the modulus squared, we're going to manipulate this maybe just a little bit, because we're going to express this in terms of sines and cosines with Euler's identity. So outside here, right, we can, I think, pretty easily say that's just 1 over the square root of a. And we have sine pi over ax. And then using Euler's identity, this is just cosine omega t minus I sine omega t. Okay. And we can do the same thing over here. So sine 2 pi a x. Now we're going to have a 4 omega t minus I sine 4 omega t. Okay. Awesome. So now what I want to do is I'm going to distribute these sine terms. And I'm just going to separate the real part and the imaginary parts. So let's do that. It's a lot of legwork for this problem, but sometimes that's okay. It's kind of relaxing. So again, we're just distributing our sine. Nothing else. Nothing more. And again, I'm going to group this. So the first part is my real term. So I'm actually going to just take this part here. Nothing wrong with that. Just how I group my terms together. So those are the two real parts. And then the imaginary part, they'll all have a minus I term, so I'm just going to factor that out. And I'll have sine pi over ax sine omega t coming from over here. And then plus, just making sure my sine is all worked out. They look fine, I think. And then sine 4 omega t. Of course, that's all over there. Okay, so now we get to do the lovely task of squaring this. So what I'm going to do, it's a little bit of a shortcut here, but first off, this will turn into a 1 over a, right, since it's that part. What I'm going to do is I'm going to kind of group this real section off. And I'm going to get rid of this. Put a big parentheses here for that. So we have this term. I'm just going to copy this part down here. And we're going to go ahead and just multiply this. Some of this I think you can do in your head. And some of this I can see simplifies. But I just want to write all this out. So if that's psi, this part will be plus I. Because remember, we're doing technically psi star psi, but that's okay in this case. I guess if you really wanted to, you could say that this is a plus and this is a minus. So now you're doing psi star psi. You just really have to be careful with that whenever you have an operator stuck in between, because that's not necessarily the same thing as this. These are not necessarily equal. So just a little good good habit there. Hopefully I didn't lose anybody with that step. Just trying to not hate my life distributing all that. Okay. Oh boy. So, I'm going to multiply these out. Now, I just want to explain my thought process. Because of the change in signs here, your cross terms are going to cancel. So essentially you're going to have your real part squared plus your imaginary part squared. And the other terms will cancel. If you're uncomfortable with that, you can distribute all of this out if you want, but I'm going to try to make this a little less of a headache. Okay, so let's square the first term. And we have cosine squared omega t. Okay. So I'm just multiplying this stuff out, nothing too crazy. Obviously this is very messy, but I think at this point everyone is okay with this for omega t. Now we're going to have this part squared. So we're squaring this part. This part's kind of boring, to be honest. And I don't even really want to talk about anything else because I'm afraid that I'm going to make a mistake if I get distracted. Because I'm very mistake prone. So far, I think I'm doing okay, though. Okay, and then the exact same thing, but with our imaginary part. So very similar, just our sines, our cosines are now sines. So, and that'll work out very well, because of course Pythagorean's identity is going to pop up here, it looks like. Almost done. One more little line of work. And then I think it'll clean up pretty nicely. This is by far the worst part of the problem. So now we're going to get our 2 pi term here. This is definitely a problem where you can be prone to make a silly mistake. Forces you to be disciplined, which is a good thing, I guess. Okay. So, oops. So hopefully you'll see that I don't really like the highlighter. We'll do this. I like this color. So hopefully you see that this term, you could factor out that sine squared pi over ax, and that's a Pythagorean identity. And by the same argument, this term and this term, no, I don't need series help. Go away. I'm okay. And I'm just talking about these parts. we can simplify that greatly. So we'll get sine squared pi over ax plus sine squared 2 pi over ax plus, now if we look at these parts, so everything to the right of that red line, so I'm going to just box this part, everything inside that red part. There's some different terms, but hopefully you will see that both those terms have a sine pi over ax and a sine 2 pi over ax. So why don't we just factor that out? Sine pi over ax, sine 2 pi over ax. And then what are we left with? Looks like 2 cosine of omega t cosine of 4 omega t. So the omega terms, if you will, there's 2 of these, right? And we're going to be left with this and this, this and this, and there's 2 of them. And then for the sine term, we'll be left with basically the exact same thing, but instead of cosine, it's sine. Oops. Okay. Well, we could factor out that 2, so let's do that. And let's also not forget there is our normalization constant out here somewhere, right? 1 over a. There we go. Yeah, that thing's going to be annoying. Maybe I'll turn it off. I never use it. So there's not really much reason for me to even have it. So again, all I'm doing here is factoring out a 2. And then I'm left with, well, I mean, you can see what I'm left with, right? It'll just be the cosine term and the sine term. Now there's a trig identity I want to bring to your attention, which is cos of a, not cos, cosine of a, cosine b, plus sine a, sine b. Maybe you remember this one, maybe you don't, but this is equivalent to cosine a minus b. Okay, so a is equal to 4 omega t, and b is just omega t. So this whole thing actually just simplifies to cosine 3 omega t. Okay. So this is our modulus squared term. Awesome. So the next part, that was the worst part of the problem. So now it gets a little bit better. Well, I say a little bit. This one is kind of messy. So essentially what we need to do for calculating the expectation value of x, so the expectation value of x is x times what we just found. So I'm just going to So we're using what we found in the previous problem to set up this integral. We'll do this. Okay. Now, you could distribute this x to all these terms, and you would have three integrals which are doable, but kind of talked about this in a previous video. You have to consider if that's something valuable to your time to do those integrals. This isn't a calculus class. You've already taken courses in that, so you've shown that you can do these integrals if someone really wanted you to, and you could probably play around with this and get really close, but I think it's unlikely this will be something you'd have to do on an exam. Most professors will give you an integral table or allow access to like an integral calculator or something. Either way, I'm not going to work out the steps here for that. What I will say is you should get the following answer after you either work that out by hand, or why is my iPad doing that? Just try to get this done before my iPad does whatever it is it does. You should get this, which, just using a little bit of algebra, simplifies to a over 2, distributing the 1 over a and adding our like terms. 1 minus 32 over 9 pi squared cosine of 3 omega t. Okay. Awesome. So, now what? Well, the amplitude, if we distribute this, is going to be 32 over 9 pi squared times a over 2, which is 16a over 9 pi squared. So you could do that to get the amplitude. And then our oscillation is just 3 omega, which, if you remember how we defined omega, what feels like forever ago, well, I didn't define it, the problem told us to do that. This is then just 3 pi squared h bar over 2m a squared. And we can see that that oscillation is not greater than a over 2. Okay, so that's that part. D is find the expectation value of momentum. And we're not going to do that integral again. We're going to use this handy formula. I think we even proved this in one of our problems, I want to say. So this is our expectation value of x. We just have to take a time derivative of that. So really just the time derivative of the cosine part. So what do we get? M times 16a over 9 pi squared times, this is a negative actually because of the negative out front, but then we get a negative from our cosine going to sine. The derivative of that is negative. And don't forget the 3 omega from the chain rule. Sine 3 omega t. That's actually going to be positive. And we're going to have 16 ma over 3 pi squared omega sine 3 omega t. And of course, if you wanted to, you could plug in what we know for omega. So 16 ma over 3 pi squared times our pi squared h bar over 2 ma squared times sine of 3 omega t, which, if you do that, that simplifies nicely to 8 over 3a h bar sine of 3 omega t. So that's our expectation value for momentum. And then finally, and again, these parts are much easier. E1, so these are the values we're expecting from E. This is part E of the problem. E1 will just be pi squared h bar squared over 2ma squared, since n is equal to 1. And then for E2, you're going to have a 4 in the numerator, but because of this 2 in the denominator, you'll just have a 2 in the numerator. So we'll have 2 pi squared h bar squared over ma squared. So for part E, it says, just to remind ourselves, if you measure the energy, what values might you get? Those. And what is the probability of getting each of them? Well, the probability is just that A term, since both of them have the same A, is going to be 1 over 2, so 50%. So 50% each. That's basically a conceptual question. So then, the expectation value of our Hamiltonian is just going to be 1/2, which is our weighted coefficient, plus E1 plus E2. Because remember, this is our sum over n of C sub n, E sub n. In this case, we go from n equals 1 to 2, and C sub 1 equals C sub 2 equals 1/2. And then you can plug these in here. And if you do that and simplify, you should get 5 pi squared h bar squared over 4m a squared. So that's how you approach this problem. I hope this helped in some way. It was a little tedious at times, but I'm hoping the way that I did this helped. If it did help you, I'd really appreciate it if you'd like the video and subscribe to the channel. And I'll definitely be posting more videos soon.